So same rules apply this time as last time. No calculators that have an integral button. If some of you have a calculator with an integral button and some of you don't, that's not fair. So no calculator with an integral button. No phones, of course. So let's get to the stuff. So these are just the questions from the MyMathLab assignment, bless you, for reviewing for exam 2. So you can do these same exact problems or variations of them in MyMathLab as many times as you feel like you need. Another thing that I was helping Selen in my office earlier, a couple days ago, do you know that if you want to go back and rework problems from an assignment, you can do that by going through the gradebook? Everybody knows that? So if you go into the gradebook, instead of the assignment tool, you can click on that review button and you can go back in and work the problems again if you want, and it doesn't change your score or anything. Okay, so let's get back to basics. Back to basics. This is a reverse chain rule problem. Hopefully you're all seeing that instantly. If we have a power, we can use the power rule. And so we will take the base of this, which is 2x minus 1, add 1 to the exponent, divide by the new exponent, and then divide by the derivative of what's inside. So that is power rule in conjunction with reverse chain rule. So if we wanted to simplify this, there's not a lot we could do, but we could eliminate the negative exponent. A lot of times we like to get rid of negative exponents. So that would be sort of the form that you would see most likely in an answer key. Okay, all good? Any part of that you're not sure of? Because this is kind of a foundation from 6-1. Reverse chain rule stuff. Negative exponent stuff. Anytime we have a negative exponent, we want to get rid of it if we're trying to integrate. So what can we multiply by to get rid of that negative exponent?
Positive.
Another negative one?
Yeah. Oh, wait a minute.
This guy. We're going to multiply by the reciprocal. Mr. Stewart.
Total guess.
Total guess, great. That only goes so far, right? So we multiply by the reciprocal. Is everybody clear that e to the minus 4x and e to the 4x are reciprocals? Right? Reciprocals. So if we have something like 4, its reciprocal is 1/4, and the property that we're using is that a number times its reciprocal is 1, or a function times its reciprocal is 1. Anytime you multiply something with its reciprocal, you get 1. So let's see how that works over here. So e to the 4x times e to the 4x is e to the 8x. E to the 4x times e to the 4x is e to the 8x. You add exponents. And so e to the 4x times e to the negative 4x is e to the 0. E to the 0 is 1. Do you agree?
Yes.
E to the 4x, e to the negative 4x is going to multiply to 1. This is almost in log form. The denominator's derivative, of course, the derivative of 3 is 0, so that doesn't matter. Over here, the derivative of e to the 8x is e to the 8x times 8. So we do our multiplication by one thing, and then we now have it in log form. And once it's in log form, we integrate to natural log, absolute value of the denominator.
You could still
still do U sub on that at the very end, right? And you'll get the same thing.
Yeah, if you have so much time to burn and you want to do it longer, absolutely. Absolutely, you could do it. What would you let U equal?
It'd be e to the 8x minus 3, right?
Correct. Yeah, so we'll let U be the denominator, and then we'll take the derivative, substitute it in, and we'll end up with the same thing. Absolutely. Yeah. Good. Good. All right. Why would we complete the square here?
Because 50 is nice.
Alex?
Because you can split off the 50 into...
So let me say, so if this was factorable, would we want to complete the square?
No.
No. If it's factorable, what technique would we use?
Boil.
The fractions.
PFD, partial fraction decomposition. If the denominator is factorable, it's going to be a lot faster to do a PFD thing than a complete the square and do like a trig sub or inverse trig or whatever. So if you can factor the denominator, going PFD is the move. But if you have a quadratic in the denominator that's not factorable, that's when we complete the square. So the answer to my original question was, why would we complete the square? Because it's not factorable. If it's factorable, we want to go partial fraction decomp. So not factorable. So we complete the square. How much do we have to borrow from the 50?
1.
1. So we're going to make this x squared minus 2x plus 1 plus 49.
What was the process we used?
Divide by 2 and square. So you take the coefficient of x, divide it by 2, and square. So negative 1, quantity squared is positive 1. And then this puts it in this form where we have a sum of squares in the denominator. Anytime we see these sums or differences of squares, the best strategy is to try to make it a sum or difference of squares with a 1. If we can make it a sum or difference of squares with a 1, that's going to make things a lot easier. So what are we going to factor out?
149.
Yeah, the 49 comes out in the denominator, so it'll come out in front as a 149. And then in here, there is no 49 in this first term. Now we want to write it as a single square. So what's going to go in the denominator? 7, yeah. And now we have two choices. You could, hopefully you recognize that it's in which form?
Inverse tan.
Inverse tan form. It's in inverse tan form. We don't have to do trig substitution. It's already in inverse tan form. If we wanted to do trig sub, we would do tangent, and we'd get the same answer. So here's another one of those things. If we don't see that it's in arctan form, but we recognize that you could use trig sub with a tangent, you'll get the same answer. It's not a big deal. But it's a lot faster if you recognize that this is in arctangent form. It's going to be way quicker just to do it. So a little gap for RCR. RCR gap. This will be arctangent of what?
X minus 1 over 7.
So whatever's in the parentheses, whatever you have in the parentheses, that's going to be what's inside of the arctangent function. So that, plus a constant of integration. And then what's going to go in the RCR spot?
7.
So we're dividing by 1/7, so we're going to have a 7 inside there. And everybody clear on where we're getting the 1/7 and the 7? If we look at that, the derivative of that is 1/7. Right, if you were to explode this out and say, okay, let's rewrite this. This is 1/7 x minus 1.
Why do you have x minus 7 over 7?
X minus 1, thank you. Thank you. X minus 1 over 7. So if we were to take that little inside parentheses thing right there, everyone clear? That's the derivative for 1/7 x minus 1/7. The derivative is the coefficient of x when we have a linear factor. So we divide by a 7th, which means multiply by 7. Integration by parts. What would we let u equal here, and what would we let dv equal?
U equals X.
So I hear u equals x.
Yep.
We hear agreement, and that's correct. We don't want to put the x with dv because when we integrate it, we'll get x squared over 2, and it will get worse. Now, sometimes we will do that. Sometimes we will. There's one case in particular where we will do that. What is the integral of e to the 4x?
E to the 4x divided by 1/4, or times 1/4.
Times 1/4 or divided by 4, yeah. So that is our v. And that, hopefully, and now be careful on your tests. I'm going to be a little stricter this time with notation. Make sure you're putting in your dx's here. That's an important piece of this. I'm not going to call anyone out. So then we're going to do our ultraviolet voodoo. So UV, that's the main diagonal right here. There's our UV minus the bottom row. So U times V is 1/4 x e to the 4x UV minus integral of v to u. And that is where we notice whether we chose properly in the original integration by parts. If this integral is harder, then we did something wrong. But that integral is easier because now there's an x missing. And the integral of this is going to be itself divided by the derivative of the exponent. So we're going to divide by 4, which will give us a denominator of 16. Make sense? All right. Yeah?
Do we have to factor out anything? Here.
Because we have that constant of integration, if we want to factor, we want to factor out of everything, not just 2 of the 3 terms. So factoring doesn't make sense here because we can't factor something common to every term. Right? The whole power of factoring is that if you pull it out of all terms, you turn it into multiplication, and then you can find zeros. That's why we would factor, because we could find zeros. But we can't factor because there's nothing common for all 3 terms. So integration by parts with a twist. I think we probably should do one.
Yes.
We'll just do one. One will be enough, right? This will be the last time you'll need to see it. Now, it's just all going to coalesce right now.
We see it all in the test, and we just write down the actual integral.
You're going to be able to kill it on the test. All right, so with a twist, when you have an exponential and a sine or cosine, it doesn't matter which one you put with u and which one you put with dv. It's not going to matter. So let's go through this very carefully, make sure that we see all the steps. All right. So on the left, we're differentiating. When we differentiate an exponential, it is itself. We always start with itself. And then we multiply by the derivative of the exponent. Dx. All right, everyone okay with chain rule? Derivative of exponential, itself times derivative exponent. Now over here, we're integrating. We integrate dv to get v. We integrate cosine to get sine. And then we also divide by 2 for reverse chain rule. RCR. Reverse chain rule. And now we're ready for the voodoo. Ultraviolet voodoo, not just voodoo. So this will be 1/2 e to the 3x times sine of 2x. And we usually write it in that order. Usually we put the exponential in front of sine, so it doesn't look like it's part of the angle. So So we usually write constant and then exponential and then trig function. Okay, so uv minus the integral of v du. Now when you look across the bottom here, so there's our main diagonal, there's our bottom row. When we look across here and multiply, there's a coefficient of 3/2. And you could put that 3/2 right here in front. It's totally fine. The problem is that you're going to have to do integration by parts again, and it will have to be distributed across 2 terms later. So my recommendation is just leave everything inside the integral. There'll be less distribution later, which will make your life easier unless you are like a hyper accountant type. Which, believe it or not, there are people like that. There are hyper accountants out there. But if you want to try to play it safe, it's usually going to give you less trouble if you leave the constant on the inside. All right, so now we're going to do integration by parts a second time. And we want to be consistent. So if we let u be the exponential originally, we want to stick with that. And so I'm going to put that 3/2 right here. This is going to be part of the exponential, so that's the first function, and there's the second function. Integration by parts usually is for a product. So there's the product. So we're going to do this. So there is our setup. There's our UDV. The derivative of u will be 9/2 e to the 3x times dx. The integral of sine 2x is minus sine of minus cosine of 2x divided by 2. All right. So let's see. I'm going to write down below here. So let me just start over. So we have, I'm going to move this whole thing over. Let's put it right there. And then let's put this up here. Okay. So omega will let be the original integral. So that's going to be 1/2. We still have this leading function here. All right, so now let's be careful. So normally we are doing uv minus integral of v du. So we have uv minus integral v du. But notice that there is a leading minus. A minus in front of that integral. That minus is going to distribute here and give us a minus uv plus the integral of v du, if we distribute that minus. So that's going to be minus uv plus integral of v du. So that's the case that we're in. All right, everyone okay with that? So, so there's that minus, and then here's uv. Now uv is negative, so minus a minus is positive. So that's going to make us plus 3/4 e to the 3x cosine 2x. Everyone agree with that? So uv is negative, and negative makes it a positive. All right, so now we're right here, so it's plus the integral of v du. So plus the integral of v du. V du happens to be negative. We have 9/2 and negative 1/2. So that's negative 9/4. If you want, you could leave it right in here for a second. If you want to do that, that's fine. Negative 9/4 e to the 3x cosine of 2x dx. Yeah,
That negative, it doesn't distribute into the integral?
this,
Yeah.
it did. It distributed right to there and made that a plus.
But it doesn't go into the, where it says v du on the integral.
In here?
Yeah,
No.
okay.
Yeah. So the VDU in this case is negative, so that negative can now come to the front. So we'll have this whole business here. That'll come down, and this will be minus 9/4 omega. Since e to the 3x cosine 2x integrated is omega. And on the left-hand side, this is 1 omega, so we could write it as 4/4 if we want to get a common denominator so we can add them together easily. And when we add, we will get 13/4 omega. And that's going to be these same things. And then we have to remember that we're going to need to include a plus c. As soon as we add that omega to the left, we need to add a plus c. Because omega is an indefinite integral, and we know that the evaluation of an indefinite integral has a plus c. And that plus c is kind of hiding within this omega here. So as soon as we move it to the other side, we need to pull it out. Make sure we have a plus c. All right, so now we multiply both sides by the reciprocal. Something times its reciprocal is 1. So we're going to multiply by 4/13.
Can we leave it on the outside? Would you want us to?
Well, there's a c in there, so you need to distribute it.
Okay.
So we have that 4/13, so we're going to have 2/13 e to the 3x sine 2x. And then 4/13 times this one. The 4's cancel. We have 3/13. 3/13 e to the 3x times cosine of 2x plus c. And again, we normally wouldn't do any factoring here because you can't factor out of the c, so it makes more sense to leave it all expanded. Yeah?
I guess I'm just confused how the 3/4 is positive and the 9/4 is negative, because I thought we had a negative in front, so.
Okay, let's look at it. Let's look at, so the original is uv minus integral of v du. That's what we're using, right? So d. Okay, so if you look in here, that part right there is going to turn into this. You agree with that?
Yes.
So whatever the sign of uv is, it will then need to be multiplied by -1. So u times v is negative, so then we multiply it by that -1 and it becomes positive there.
Mm-hmm.
And then we have to have a minus integral of v du. So if we look at v du is negative. So v du is negative, negative times negative is positive, but then we still have this minus that has to be distributed. So there's actually 3 minuses which are going to mash together, giving you that negative.
Okay.
You see it?
Yeah.
There's a lot of things flying around. You just have to sort of get to a point where you have a way to think about it and decide whether it's positive or negative. And that's our final answer. Other questions on it? Joe?
You could write that as a common denominator of 13, right?
Yeah, you could. Yeah, you could combine this into, yeah, you could write that as if you wanted to, yeah. Other pieces of that? Make sure you can do the twist.
I can't.
Uh-oh.
Yeah, you just completely lose me after a certain point.
Where? Show us.
Like,
Tell us exactly where you're lost.
right there.
Wait, right where?
Right there in the middle.
Right here?
Yes.
Right there?
I mean, I understand all that and where all the positives and negatives come from, but like everything after that is just.
So are you good with this?
Yes.
So that's the original UV.
Yeah.
That's the original UV. And then this one right here is the second UV, but multiplied by -1.
Mm-hmm.
So that's this one times this one times -1.
Yes.
So you're okay with that one?
Yes.
So then you're almost there.
Yes, and I understand up until that point.
So this symbol, that right there, this symbol, the integral of e to the x cosine 2x, that is what we're going to label as omega.
Right.
It's like a nickname.
I get that.
So that means right here, this negative 9/4, that's a coefficient that comes out in front.
Right.
And then we have integral e to the 3x cosine 2x, which is omega.
Right.
Wait, where are you not getting it then?
Everything after that.
So then, if we have x's on both sides, we combine them because they're like. So in this case, we have omegas on both sides, so we're going to combine them with addition
So,
because these are like.
so you take that and then you add one of those to the other side.
Yep, so we're going to add 9/4 omega to both sides.
And so you just put a 1 there in front to make it so you can add those.
Correct.
And then you have the
The new coefficient.
okay.
And then if we want to solve for, we want just 1 omega, because 1 omega is what equals the original integral, so we
So you
want.
multiply by the reciprocal.
So we multiply by the reciprocal.
And then you have the answer.
Yes.
Okay. Now I understand.
Good. Excellent. Great question.
Yeah, you mix up.
Great question. Okay, let's carry on our merry way.
Oh, no, volume is right.
So finding the volume of something using a shell or a disc or a washer. So these things still live in Calc 2. They're not gone. So let's draw a little picture. We had some issues on the first exam, drawing some basic shapes. Let's talk about this. So the e to the negative x, that is an exponential decay. E to the 0 is 1. So you know that this function goes through right there at 1. And it's exponential decay. As x goes to infinity, this goes to 0. It does not pass through the x-axis. So there is a graph of e to the negative x. And so this says we want to find a region that's bounded by e to the negative x and the x-axis. So that gives us this. And then it tells us the walls, or the left side and the right side, are from the interval 0 to natural log of 6. So we'll call that 0. We'll call that natural log of 6. So there is our region. There should be no ambiguity. If you're asked for a region, you shouldn't have to say, oh, is it this one or is it this one? There should only be one region that's trapped by all the information. If there's not one region, then there's a problem. There has to be just one region. And then this one says, let's rotate it around this line, vertical line, at x equals natural log of 6. So that's going to be our rotation. And we are going to use a vertical element. Vertical elements are at random x's. Everyone see why we wouldn't use a horizontal element?
Yes.
Right? We wouldn't use a horizontal because the right bound changes depending on where you draw that horizontal element. If you draw a horizontal element right here, the right boundary is this vertical line. If you draw the horizontal element right there, the right boundary is the exponential decay function. So we don't want to use a horizontal element because we don't have consistent left and right curves all the way through, consistent left and right boundaries. So we have to draw a vertical. That forces us to be using a cylindrical shell. And the area of a cylinder, 2 pi RH, that's the area of a cylinder. So now let's identify the radius, identify the height. So the radius is the distance from your element to the axis of rotation. That's the radius. That's what the radius means. If you're rotating around this line right there, the distance from that axis, that is the radius. That's got to be a positive number. Cannot be negative. The radius. And what is that radius?
Is it X?
No.
Natural log of 6 minus x. Right?
Yes. Bingo.
When would it just be X? Is that when it's
If it's rotating around the y-axis, so this x is measuring that distance right there.
oh if it's oh yeah.
So if we were rotating around the y-axis, then that x would also act like the radius.
Discs.
But if we're rotating around this, there's our radius, and that's a horizontal distance, so we're going to take the right x-coordinate minus the left x-coordinate. Right minus left. Natural log of 6 minus x. So this distance right in here, this distance is x. This distance right there is natural log of 6. So the radius is natural log of 6 minus x. All right. How about height?
the function.
E to the negative x. It's the function. E to the negative x. Perfect. So that is the area of the cylinder at x. And to get volume, we integrate the area. So the 2 pi can come out to the front. 2 pi integral 0 to ln of 6, ln 6 minus x e to the negative x dx. So most of us would probably distribute the e to the negative x to these two different terms and separate into two separate integrals. That would work totally fine. We might be able to do integration by parts right away, though, because we do have a product. We have natural log of 6 minus x times e to the negative x. We could try to do integration by parts right away and not do two separate integrals. Let's try it. Let's try it. So we certainly have to use integration by parts because we have an x e to the x, x e to the negative x. So let's go u equals natural log of 6 minus x. And dv will go e to the minus x dx. The derivative is negative 1. So that's negative dx. And this will be negative e to the negative x. Make sure all four corners of that grid make sense. Everything makes sense there?
How is it du equals negative dx?
The derivative of natural log of 6 is 0, because natural log of 6 is a constant.
Oh yeah, that yeah.
That makes sense? All right, so let's see how this plays out. So we're going to have this 2 pi out in front, big brackets, and now we have uv. So u is natural log of 6 minus x times v, which is negative e to the negative x. So uv minus the integral. Oh, and let me put my limits of integration in here. This is a definite integral, so we have to have our evaluation notation. So we'll evaluate from 0 to natural log of 6. So uv minus the integral of v to u.
Can we just leave the limits of integration on the outside or no?
Well, this uv part has to have some limits of integration. So we need to put them in there at least for one step. And now, isn't v to u positive? So the inside of the integral is positive, so that minus just stays right there. uv minus integral of v to u is positive. So we have e to the negative x dx. And then big bracket closes, 0 to ln 6. All right, and instead of evaluating right now, let's just evaluate at the end. So we will have 2 pi multiplied by big bracket. This minus sign right here, I'm going to move it into this thing next to it. Instead of natural log of 6 minus x, if we take that minus and push it in, it becomes x minus natural log of 6. Let's just get rid of that minus sign. we have that. We could even put the e to the negative x, we could put it in the denominator. Usually it's a little easier to evaluate things with positive exponents. So let's do that too. So let's rewrite this. Let's do that. Let's put this in the denominator. So that's going to be an e to the x. Question?
How come you did that? I'm so sorry, you kind of lost me there.
Just because. Because there's this leading minus sign. If you have three things being multiplied together, like if we have a multiplied by -1 multiplied by b, you can write that in lots of different ways. You could write this as minus ab. You could write this as minus a times b. You could write it as a times minus b. Right? All those things are equally valid. That's the associative law of multiplication.
Oh, and since it's
And since that leading minus is there, it's like, what a pain to always have to put parentheses around it. So let's just move it in here. That makes that positive x a negative natural log of 6.
Are you multiplying e to negative e to the x to x? Oh.
I'm not multiplying this. I'm going to change this exponent to positive by moving it down into the denominator.
Okay. I see what you're saying.
Right? The exponent, the sign change just moves it up and down. It's like a light switch. Right? It just switches up and down depending on whether it's on or off. And then here, the integral of e to the negative x is e to the negative x divided by -1. So that's going to be plus e to the negative x. Again, let's put it in the denominator because it's easier to evaluate things in the denominator. So we have that. And then our limits of integration are 0 to ln of 6.
Question about notation.
Yeah.
So I was watching some YouTube videos,
Yep.
and at the end of the big bracket, they just wrote the lower limit and the upper limit on the corners of it. Is that normal, or is that
That's
just-
not normal.
Okay.
That's not normal. And they had a left bracket also?
Yes.
Yeah, that's usually we wouldn't do that.
Okay.
Usually, yeah. Sometimes people will put little like things like this, but not if there's already other brackets in there. Seems a little weird. The traditional notation is just a vertical line.
So just stick with that part.
Yeah, I would do that just to be safe. I mean, I don't think anyone would be confused, but there will be people that say that's not standard notation. Yeah, that's someone trying to invent their own notation, which is fine. Sometimes it takes off. Okay, so let's see if we can simplify this easily. Plugging in the natural log of 6 first. All right. So plugging in the natural log of 6. Let's keep the bracket. Right here, ln 6 minus ln 6, 0. Plug in the ln 6 here and we get 1/6.
Yeah, one.
6 in the denominator.
Yeah.
And then we subtract off the antiderivative at 0. So plugging in 0, e to the 0 is 1. So we have a minus natural log of 6 right there. Minus natural log of 6. And then plus 1. And that's all in parentheses. So we subtracted off the antiderivative at 0. So here's the antiderivative. We plugged in 0, and we got negative natural log of 6 plus 1. And then we just simplify that one more step. We will end up with, so positive natural log of 6, and there's going to be a 2 pi out in front, positive natural log of 6, and then 1/6 minus 1. So 1 over 6 minus 6 over 6, which is minus 5 over 6. So that'll be our final answer. Is that good?
You just scroll up to your graph again.
Mm-hmm. So that's going to be the volume of this little dish when that rotates around. It's going to form a little bowl-looking thing. Okay, shells.
It's a Beyblade state.
A what?
A Beyblade state. Beyblade Stadium.
Or that, yes, yes, exactly, exactly. Yeah, it's going to be one of those stadiums that has the arched floor. It's like what's that thing that you ride the bikes in, the velodrome? It's called the velodrome. What's it called? You know, in the Olympics, they've got the stadium with the curved walls, and you're riding around the curved walls. Velodrome? Velodrome, right? Okay, so, or an ashtray. Looks like an ashtray. Do they still make ashtrays? Okay, so powers of sine and cosine. Powers of sine and cosine. What should we pull off here?
Cosine.
So the power on cosine is odd, so we're going to pull off one cosine and convert the leftovers. So the 4 can come out to the front, it's just a coefficient. And then we have sine of -3/2. We can't do anything with that, but we can pull off one cosine and put it over with the differential. And so the whole point then is that we want to let u be sine, because cosine will then be its derivative. And so that means we want everything else to be sine, so that when we let u be sine, we can replace all these sines over here. So when we pull off one cosine, we're left with 2. And what do we rewrite cosine squared as?
1 minus sine squared.
We're going to rewrite it as 1 minus sine squared. And then we can let u be sine, and du will be cosine of x dx. And so these work out, if you pick the right thing, it works out pretty easily. So we're going to have u to the minus 3/2, and then 1 minus u squared, and then du. So the sines and the cosines are the easier of the products, because all you have to do is look for an odd. And it's the same for either. If cosine has an odd power, or sine has an odd power, you do the same thing. Pull one off, convert the leftovers. And if both are even, you have to use power reduction identities. Yeek. So distribute that e to the -3/2 times 1, e to the -3/2 times, or e, why am I saying e? U to the -3/2 times u to the 2.
-1/2.
Just one.
Just what?
1/2.
1/2. Positive 1/2.
Wait.
Wait, what? Wait, what? So -1.5 plus 2 is positive 1/2. Right? -3/2 is -1.5 plus 2.0 is 0.5. Positive half.
Wait,
Yeah.
when you multiply,
You add the
powers,
exponents.
Yeah, you add them, but wouldn't it? Oh, I see. You add them like as if they were fractions, like so you wouldn't. Oh, that's
-3 over 2
I don't
and
know
4
why I
over
was
2.
thinking of that as 2 over 2.
Yeah, 4 over 2. 4 over 2.
Yeah.
4 over 2.
Yeah. Yeah. I see.
4 over 2. Yeah, exactly.
Because then that would just be u by itself.
That's right. U to the 1, right. So here we're going to add 1, so we're going to get -1/2 divided by -1/2 is multiplication by 2. Add, divide. Same thing over here, we're going to add 1. We add 1, we get 3/2 divided by 3/2. And then plus a constant of integration. And u is sine. So we're going to come back in here. This is going to be -8 over square root of sine. U to the -1/2 is a square root of u in the bottom. Minus, here we're going to have 2/3 sine raised to the 3/2 power, and then plus c.
Don't you have to multiply the second term by 4?
And we have to multiply the second term by 4. Thank you, absolutely, positively, thank you.
What if we left it like instead of having sign at the bottom, what if we just left it as sign?
Sign to the negative 1/2?
Yeah, would that be okay or no?
It's okay. It's not ideal.
Dock us for it?
No, I wouldn't tell.
Okay, that's what.
That's what you want to know.
Yeah.
Yeah.
So since they're all negative,
Usually we like to get rid of negative exponents though. Since both those are negative, what?
is there anything special you can do or no?
No. Nothing special.
What if we didn't multiply the 4 and we just points? Because I never do.
I know. As long as you write your DXs.
I never do that.
My red pen's gonna be looking for missing DXs this time.
Can I just write on the top page, DX?
DX everywhere?
There it is.
Omnipresent DXs. All right. Powers of tan and secant.
Holy crap, that's actually so much smaller.
I know. So here we have an odd on tan and an even on sec. So that means we could go either way. If secant is even, we pull 2 off and convert the leftovers, so we'd want to convert a secant squared. If tan is odd, we pull off a sectan and convert the remaining tangents. That would mean we'd have to convert 4 tangents. So we have a choice, convert 4 tangents or 2 secants. 2 secants is going to be easier than converting 4 tangents. So we'll pull off secant squared. 7 can come out to the front. Tangent to the 5th, we're just going to let it be. We're pulling off a secant squared. So that is our new differential, with the intention of letting u be
10.
tan, because the derivative of tan is sec squared. So that means we want only tangents inside these parentheses. So we've pulled off secant squared, meaning that we have the secant squared remaining. So these secants right there, they have to be converted over to tangents. And secant squared is equal to?
Tangent squared x plus 1.
Tan squared plus 1. Very good. Tangent squared of x plus 1.
Will you cringe if we write it the other way around?
No. I believe in the commutative law of addition,
Okay.
as I hope you do,
Sometimes. When it's convenient.
when it's convenient. All right. So now we can, if you want, you can distribute before you do the u sub, but it's a little easier to just be dealing with u's when you start distributing. So I think it's better to convert to u's before you distribute. But it doesn't matter. Whatever you believe in. So u to the 7 plus u to the 5 du. And these integrals always end up just being integrals of powers of u, so not anything too complicated. So u to the 8 over 8 plus u to the 6 over 6 plus c. Distribute the 7, replace the u with a tan. So we're going to get 7 over 8 tan to the 8. 7 over 6 tan to the 6. We'll see. Not too bad. Much easier after you've done a handful of them, right?
Yeah.
And when we first talked about it, your eyes looked crossed when we were doing these. They do not look crossed anymore. Yeah, let's go here. So this one is not very different, right? There's only one thing you could do here. The only thing we could do is pull off a secant squared and convert the leftovers. That's all we can do. So let's do it real quick, or at least set it up. Since it's identical to the last one, maybe we won't go all the way through it. So that would be our next step. We pull two secants off. That's going to be grouped with the differential. Those two are grouped with the differential over here, with the intention of letting u be tangent. And if we let u be tangent, then du is secant squared. So that's going to be 8 integral of u to the 1/2 multiplied by 1 plus u squared du. And kind of same move now. We want to distribute that u to the 1/2, get powers of u, and then use the power rule. So we're going to have 8 integral u to the 1/2. U to the 1/2 plus u to the what? 5 halves. 5 halves. So we'll end up with plug in tangent and distribute. And we're good. So we're going to have 16 divided by 3, tangent raised to the 3/2 power. 16 divided by 7, tangent raised to the 7/2 power. That is a 7. Plus e. You know what this means?
Yes.
We're almost a power series.
Don't we have to break a few parts?
Almost an infinite series. That's shocking. We are halfway through the semester.
What?
More than halfway through the semester after today. Wow. So maybe we're exactly halfway through. I think we're exactly halfway through after today. Nuts. Nuts, nuts, nuts. Let's do one more and then we'll take a break.
Oh, that's true.
Trig sub. We'll do one trig sub, take a break, and then do another trig sub.
Oh, yes.
So trig sub, we see a difference of squares. We want to make it a difference of squares with a 1, because that makes life easier. It's true.
Is that 13?
13 squared would end in a 9. 14 squared would end in a 6. So 14 squared. So we're going to pull out a 14. So that square root is being attached to the 196. The square root of 196 is 14. And then inside we still have the x squared, and down below we're going to have 1 minus x divided by
14.
14 quantity squared. There. As soon as we have that 1, we're ready to do trig sub. The power of trig sub.
Sine.
Yep.
Sine.
Yep.
Y'all have your physics test today?
Yes.
How'd it go? I talked to someone earlier today who decided to just not take the test. I was like, oh, that's one option, I guess.
What physics?
Physics 1.
Which one?
Like calc-based or
Calc
just
or
regular?
algebra?
Calc base.
Oh.
Calc base. Like, oh, you're just not going to take the test.
Is it that bad?
I don't know.
Depends who you have.
When did he leave?
Okay, so we're going to let sine be whatever we have in parentheses. So sine is going to be the x over 14. And remember, the whole point of using sine is that then 1 minus sine squared is cosine squared. And the square root of cosine squared is cosine. So that's going to be that's our whole plan. So let's see how our plan unfolds. In the numerator, we have x squared. So if we look right here, x is 14 sine of theta. If we square it, we get 196. Or you could just write it as 14 squared. It doesn't matter because we're about to cancel a 14. Sine squared. 14 squared sine squared. And then dx is 14 cosine theta d theta. Oh, there's another 14. Down below, we have square root 1 minus sine squared. And this cosine right there, and this whole denominator, those are equal, so they cancel. 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. And those cancel. We can also cancel one of the 14s with the denominator. So we're going to end up with 196 out in front from that 14 squared. I'm going to cancel these two. So we're going to have 196 out in front. It looks like the only thing left is sine squared in there.
Yeah.
Okay.
Can this be on the top? Like this, or you can't.
How do we integrate sine squared? Power reduce? Power reduce. Power.
1 minus cosine 2 theta.
1 minus cosine 2 theta
Divided by 2.
divided by 2.
But then you have to change the cosine to theta.
Now we can integrate. As soon as the power is reduced, then we can integrate directly.
It is always cosine.
Question?
You just can't integral sine squared theta?
I wish! Freshman dream!
I know.
What, do you want to make it sine cubed over 3?
Never mind.
Now, if it was x squared, we would do that. Do x cubed over 3. But if it's a sine squared, the only way to integrate is to power reduce it. So sine squared, power reduce, cosine squared, power reduce. Yeah.
And if it's cosine, that becomes a positive, right? And it'll-
If this was cosine squared, that would be a positive.
If it's sine.
Okay, what is 196 divided by 2?
98. Theta.
98. Integral of 1 is theta. Integral of cosine is sine. Now, sine of 2 theta, we do not have any information on 2 theta. So we have to use a trig identity to get rid of that sine 2 theta. We need everything to be sine or cosine 1 theta. So what identity do we use?
Is it the 2 cosine sine?
So sine of 2 theta, the double angle identity for that is 2 sine theta cosine theta.
Oh, okay.
Wait, what's the one for cosine?
Cosine 2
Are
theta
we gonna
is,
see it?
no,
Okay.
cosine squared minus sine squared.
Oh,
This is the one we tend to see more, and we'll see that other one later, but not in this chapter so much. So those 2's cancel. Time for our cool triangle. We get to draw. All you creative types, you get to draw a triangle. Whoa. Yo. Okay. Sine of theta is x over 14. So we get that. Get to draw a picture. Draw it nicely. What's the other side?
root x squared minus.
No.
196 minus x.
Yes.
Oh,
Hypotenuse squared first.
fine.
Long side first. The longer one has to go first, or you'll have a negative. Very good. You're almost there. Where? What is theta?
Sine angle.
Tan X minus
Oh,
one.
what's the
Sine
sine?
X over 14.
Sine of theta, if we look at our triangles, x over 14. Cosine of theta is the square root over 14. Let's see. So the only thing we could do now is distribute the 98. Questions?
You wouldn't combine the two fractions right here?
The 14s, yeah.
Yeah.
So we would distribute the 19 and simplify with that. Yeah, so 14 times 14 and then cancel any common factor. So we would end up with 98 inverse sine. And then 98 divided by 196, whatever that simplifies to. Somebody tell me what that simplifies to. Anyone know 98 over 14s?
Take a guess.
Take a guess. So divide by 2 first, because that's going to be 49. 7 goes into there once, 7 goes into there 7 times. 7 goes into there once, 7 goes into there twice. 1/2.
Oh, okay.
That would be a good guess.
So would you dock us points if we just left it at that point? I want to make sure, man. I'm trying to get all my points as I can.
Right here?
Yeah, if we left it like that, you dock us? Say no, please.
I'm going to be looking for DXs and things like that, so I wouldn't dock you for that.
Okay, thank you.
Yeah.
Eventually gonna be X after that.
All right, let's take a break. I need a break from you. Let's take a break. Let's take a break. Because Gerardo said, where is the magic pen? Okay, so let's take a look at this one. Okay, what technique are we going to use for this type of madness? I know, right? So, is it a proper fraction or is it improper?
Improper.
Improper. So if it's improper, we long divide. So we're going to take x squared plus 64, we're going to divide it into x to the 4th.
That wasn't even the first step.
There are other ways, but this is generally the fastest. If you have an improper fraction, it's going to be fastest in almost all cases to use long division. So x squared goes into x to the 4th, x squared times. Question?
So say if you didn't notice that and you just went straight to trig substitution, would it still work or no?
You could get to a trig sub. It'd be pretty long,
Okay.
but you could get to it. Yeah, you could get to it though. So then this is minus 64x squared. And then how many times does x squared go into minus 64x squared? Minus 64? So then we're going to have minus 64x squared minus whatever 64 squared is. We'll just write it like that for a second. And then we're subtracting, so this becomes plus 64 squared. So our integrand becomes the quotient plus the remainder divided by the divisor. So that is the best way to handle that thing. Long divide first. And then it unravels fairly nicely because the x squared integrates immediately. This 64 integrates immediately. And now let's deal with this part. So in the numerator, we factor out 64 squared so that we just have a dx. And what are we going to factor out of the denominator to make a 1?
164.
Pull out that 64 in the denominator. So then this is going to be x divided by 8 squared plus 1. So there's no 64 here, So we can think of introducing a 64, top and bottom. And this 64 and that 64 factor out to be that. And then x squared over 64 is x over 8 squared. And now it's in which form? Arctan. And so now we are good to go. It is in a form that we know how to take the antiderivative of. So we have x cubed over 3 minus 64x. One of those 64's cancels. Never even had to deal with it. And now leave a blank for reverse chain rule, because we see that it's not just x squared plus 1 in the denominator, it's x over 8 squared plus 1. So we know there's going to be a reverse chain rule. So it's going to be an arctangent of x divided by 8. Dividing by 1/8 means multiplying by 8.
Actually, that's 8 cubed.
And yeah, that's 8 cubed. Does that make sense? Any step there? So the only simplification step would be to multiply the 64 by the 8. Yeah.
How do you know you had to do the
Top heavy.
dividing?
Top heavy. If
But
the denominator has a smaller power than the numerator, it's top heavy, so you have to divide it.
wait, was the last one that we did not like that?
I don't think we've done a long division today, have we? What last one?
The tricks,
Tricks over right here?
or were they the same? They were the same.
Well, this has a square root, though. You only do long division if you have a rational function. If you have a polynomial over a polynomial. You don't want to be doing long division with square roots. All right? No, don't do long division with square roots. Only if it's a polynomial over a polynomial and the polynomial in the denominator has a lower degree. Or equal degree. Lower or equal. The only way it's proper is if the top is smaller. It's the only way it's equal. Okay. So, this one's a long division. Let's label it long division because, all right, we did, let's do another trig sub. Should we do a secant one?
Sure.
Yeah.
Yeah. Let's do a secant one. So if we have a sum of squares, it's tangent. If we have a difference of squares, it's either sine or secant. And here we're going to create a difference of squares with a trailing 1. That is secant. So we're going to factor out that 400 because we want a difference of squares with a 1. And that 400 is in the denominator. What should the exponent on that 400 be? 3/2. So if we just had a square root in the denominator, we'd have a square root of 400. Whatever the power is, has to come along. And then, in the denominator, we have quantity to the 3/2. It's going to be a -1. This is going to be x divided by what quantity squared? X divided by 20 quantity squared. Because 20 squared is 400. All right. Any questions?
Isn't that going to be secant?
Say again?
Isn't that going to be secant?
Yeah, we're going to use secant. Yep, that's the next step. Secant. Let's go with secant. So we have a difference of squares with a trailing 1. That's secant. Difference of squares with a leading 1 would be sine. So if it was reversed, if it was 1 minus, then we'd do sine. Derivative of both sides with differentials. So that's our derivative. Now we need to replace all the x's, all the dx's We need to convert everything to theta. Must convert to theta. Square root of 400 is 20. 20 cubed. We'll just leave it at that for a moment. 1 over 20 cubed. Integral. We come down here and we see our dx. There's dx. That's going to be 20 secant theta tangent theta d theta. 20 secant theta tangent theta d theta. And then right here we have secant squared minus 1. So let's write that one more step before we simplify. And what is secant squared minus 1? Tangent squared. So this part in here, tan squared. Which is the whole point of trig substitution. Take two terms and turn them into one. Take two and make one. Okay. Another 20 in the numerator, that'll cancel, so we'll end up with 1/400th out in the front. In the numerator, we have secant tangent. In the denominator, let's see what we have. That's tangent squared raised to the 3/2. So that's going to give us tangent cubed in the denominator. Marvelous. One of those tangents cancels, correct? So we're going to be left with secant over tangent squared. So that's not meeting one of our things. For tangents and secants, the two things are secant to an even or tangent to an odd. Doesn't meet that. If it doesn't meet that, we have two choices. We go to a Pythagorean theorem or we convert to sines and cosines. Now, converting to sines and cosines makes the most sense because the tan squared is the only thing we could convert with a Pythagorean. And converting tan squared to sec squared minus 1 takes the denominator as one term and makes it 2, which is bad. We do not want the denominator to have two terms. Having the denominator be one term was our whole goal. Here we had two terms. We want to combine it down into one term. So going to sines and cosines is the correct move here. So this will be a 400th integral. Secant is 1 over cosine. Tangent is sine over cosine, but then we flip it. So we have cosine squared divided by sine squared. And one of the cosines cancels. So now we have sines and cosines. And that cosine is to an odd power. So we just imagine it with the differential. And what do we let u equal?
Sine.
Sine. Bada bing. So if we let u be sine, we have a sine squared down in the denominator. So that's going to be a u squared in the denominator. So we're going to have integral of u to the negative 2 du. Cosine of theta d theta, that's becoming du. Sine squared becomes u squared, but it's in the bottom. So we pop it up top by changing the sign. That's a power. How do we integrate that? Power rule. Add 1, divide. So we're going to add 1 and divide by the new exponent. This was not definite integral. So minus 1 youth. Minus 1 over u. 1 youth. Youths these days. These darn youths. Okay, so then minus 1 over 400 multiplied by 1 over sine, which you could write as cosecant if you want.
No.
No, 1 over sine. We have to go to our cool triangle anyway.
What?
What?
Can't just leave it as 1 over 400 sine theta plus 8.
Blah, blah, blah. So secant of theta is x over 20. Secant of theta is hypotenuse over adjacent. So what is that vertical side?
The other thing, that.
Say it out
What
loud.
we started with.
X squared minus 400.
Ah, yes, thank you. So start with the hypotenuse, square that, subtract off the square of the other side. Now, we're almost there.
No, we're not.
We are almost there. Where? So 1 over sine. So sine is opposite over hypotenuse. 1 over sine is cosecant, which is hypotenuse over opposite. So it's going to be negative 1/400th, and then x divided by the square root of x squared minus 400 plus the.
Is that it?
That's it. We're there. You have arrived.
Do you always want to get it into sines and cosines?
No,
No.
not always. So this thing right here, if it was reversed, if it was tan squared over secant, then you would go Pythagorean. That would work better. But because the square is in the denominator, that's not going to help if we convert that to secant squared minus 1. So we're going to sines and cosines here because converting to the Pythagorean makes it worse. If you make the denominator 2 terms instead of 1, that's
Could you
worse.
show us how it would look like in the Pythagoreans?
With Pythagorean?
Yeah.
Yeah, we did one earlier. So if we ended up with something like this, tangent squared of theta over secant of theta. So that one doesn't match either of the two things, secant to an even or tangent to an odd. If it doesn't match one of the two things, we either go Pythagorean or convert to sines and cosines. Converting to sines and cosines would work here. But it's going to be a little faster if we convert that tangent squared to secant squared theta minus 1. So then what would we do at this stage?
Split the fraction.
Split the fraction. So if we split the fraction, we are going to have secant minus cosine d theta.
Triangle.
Integrate.
And then, yeah.
Integrate. What's the integral of secant? Natural log of tangent plus secant. So natural log, I usually write it as sec plus tan, because the derivative of secant is secant tangent, and that's what I use to remember it. And then integral of cosine of sine. So you can write it as sec plus tan or tan plus sec, because we believe in the commutative law of addition. All right, so now we will go to a triangle. Yeah. So that's what happens if we use Pythagorean. Question?
Are we gonna have to remember the natural log of secant? Like, is it gonna be part of the test like that, or?
I haven't finished the test yet, but I would remember that one.
What?
The integral of secant. Integral of secant. Know that one. Just in case. Integral of secant. Natural log of secant plus tangent.
I have a request for a problem.
Okay.
You have to look at it.
I have to. Is it that bad?
Yeah. It's just letters.
Oh, you have a request for. You want that on the test?
No, I want. Oh, like.
Oh, I thought you were
Do it.
requesting a test question.
Oh,
I'm like,
no.
I never had anyone request a test question.
No, like.
That's a cool idea.
To work on it.
Yeah, but like everybody turn in a test question of their desire, and then I'll pick at least 2 out of the bag.
Yeah, that'd be nice.
That'd be kind of cool.
Go like me to the X.
That'd be.
Everyone puts like 2 + 2.
Calculus question. No shenanigans. No shenanigans. All right, so this one is weird, according to Alex. So we've got this. Ooh. All right, so B over A. X. Okay, I think I have it. Actually, it's A squared, not X.
Which problem is it?
So this is 11. This is 8.4 number 8.458. What homework problem is that then? First one?
11.
Oh, it's
Question
11. It's question 11. Okay. Now you all know the area of an ellipse, right?
No. It's like a circle.
What's the area of a circle? Pi r squared. So here, this is B, this is A. If we had just a circle and we looked at it, isn't this like R and R?
Yeah.
And the area of that circle is pi r r,
So it's what?
pi r squared. So what do you think the area of the ellipse is?
Pi AB.
Pi AB.
Oh.
Okay, but that's what we're trying to prove. Trying to prove that it's pi AB. So this curve right here, that is the upper semi-ellipse. If we wanted to find the area, we could use some symmetry, correct? We could find the area of this and multiply it by 4. So the area of our total ellipse is going to be 4 multiplied by the integral. What are our limits of integration going to be?
0 to A.
0 to A. Because this point over here is A comma 0. So we're imagining rectangles from 0 over to A. And the function that we're integrating is B over A times this.
Zero.
All right. Everybody okay with that setup?
Sure.
JP, did you have a question?
Yes, kind of wondering why is it 4?
So this curve right here, if we integrate the curve from 0 to A, it's just going to give the area between the x-axis and the curve. So then we're going to quadruple it to get the whole ellipse. Okay, so B over A is constant, so that's coming to the front. So we get 4B divided by A. Integral 0 to A. But we want to make this a difference of squares with a 1, so what are we going to factor out of the inside?
A squared?
A squared is going to be factored out of the inside. And what's the square root of A squared?
A.
1A. So we're going to put that A coming out to the front right there. Integral square root 1. So this is going to be x divided by A quantity squared dx.
I see it now.
You see it?
Yeah.
So those A's cancel. And what are you going to let x over A equal? Sine of theta. So x over A will be sine theta. And 1 over A dx will equal cosine theta d theta. So we're going to convert over trig sub. We'll have 4b integral. Let's just put placeholders. So this will be 1 minus sine squared of theta. And what's dx equal to? A cosine theta d theta, right from here. Multiply both sides by A. So now that A over there is going to pop to the front. So we get 4AB And what's left inside the integral? Cosine squared. Right? Because square is sine, 1 minus sine squared is cosine squared, square root of cosine squared is cosine, cosine times cosine.
Cosine.
Cosine times cosine. Okay. Now what do?
Power reduction.
Power reduction. So we're going to divide by 2, which is going to give us a 2ab out in front. And is it 1 plus or minus?
Plus.
Plus cosine of 2 theta. 2 theta. And now we can integrate. So let's get all the way over here. So 2ab theta. Integral of 1 is theta. Integral of cosine is sine of 2 theta. Divided by 2. Placeholder limits. And what do we do with that sine of 2 theta?
Different identity, so it's gonna be 2.
Sine.
2 sine cosine.
2 sine cosine. 2 sine cosine. Oh boy. So 2 sine cosine, the 2's cancel. Placeholder limits for one more moment. 2's go gone. All right, now to get back, got to get back. Go to our triangle. Sine of theta, x over a. Missing side,
A squared,
square root a squared minus x squared.
that, yeah.
Yeah, that. Square root of hypotenuse squared minus leg squared. That thing. So 2ab, what about theta? What's theta equal to?
Inverse tan.
Inverse sine, x over a. Inverse sine, x over a. So then we're over at that part right there. Sine of theta is x over a. Cosine of theta is adjacent over hypotenuse. So that's the square root expression over a. Square root a squared minus x squared, all divided by a. Back to our original limits, 0 to a. And what happens when we plug in a?
That?
So plugging in a here, inverse sine of 1.
What's A? Oh,
A is just that limit of integration.
She's getting.
So angle that has a sine value of 1,
90 degrees.
90 degrees, pi over 2.
oh.
Plug in a equals, x equals a here, and we get
0.
0. Okay. Now we subtract off the antiderivative at 0. Inverse sine of 0, angle with sine 0.
0.
0, angle with sine of 0, y coordinate is the sine. So angle with sine 0 is 0, so that's gone. Plug in 0 here. Gone. So that's, well, let's just leave it as a minus 0. And there is our area. Pi AB. Just like a circle, pi RR. Lovely, lovely. Wow, it feels anticlimactic, even though it's not.
My brain's gone already.
I think it's.
Went to bed.
Don't put one like this on the exam.
So this is the one Alex wants to have put on the exam.
No.
Yeah.
No, not that one.
No.
All right, so yeah, so it can feel very overwhelming because it's all letters in there.
Yeah.
But if you remember that they're constants, you treat them like constants, and it's it's just like a normal trig sub. All right, one more trig sub. Do a tangent one.
Please, no. We already did tangent one, didn't we?
No, we didn't.
I thought we did.
No, I didn't. Did you?
What?
We did not do a trig sub with tangent yet.
Not even the log division one? The log division one, can't we go?
Oh, yeah, maybe we did okay. Well, this one will be fast.
You say
Trig sub is fast.
Uh-huh.
Said no one.
I am losing these.
Okay, so pulling out the 81, and the 81 is jumping through a square root, so it gets square rooted. In the denominator, we have the square root of 1 plus x over 9 squared. It's all becoming clear. And because it's a plus, we use tangent. So we're going to say x ninths is equal to tangent of theta. Take the derivative of both sides. And we get that. All right, so now the part that tends to cause trouble, but it shouldn't. So x squared. When we look for x, we look right here and we see that x is 9 tan theta. So if we square 9 tan theta, we'll have 81 tan squared theta. dx, we look for dx, that's down here. dx would be 9 secant squared of theta d theta. So multiply by 9 secant squared of theta d theta.
And just turn to secant squared in the denominator.
And down in the denominator, 1 plus secant squared.
What?
All right, 1 plus tangent squared, thank you.
Did you see?
So 1 plus tangent squared is secant squared. The square root of secant squared is secant. So this denominator is going to take out this 2 and make it a 1. So that's going to cancel with that and make a 1. We have a secant up top that cancels with that whole denominator. We have a 9 that cancels right there. So we'll end up with 81 in front. And I think all we're left with is tan squared times secant. And that doesn't meet either of our conditions. Secant's not to the even power, tangent's not to the odd power. So we have two choices, Pythagorean or sines and cosines. Does not matter which way we go usually. Changing to sines and cosines is going to leave us with a sine squared over cosine cubed. Go that way. Or we could convert tangents to secant squared minus 1. Let's go to sines and cosines and see what happens.
Which one would you recommend?
You know, sines and cosines are always easier to deal with. So if you have a choice, you know, unless there's an obvious Pythagorean simplification that's going to work, sines and cosines is good. Okay, so we're going to have sine squared over cosine cubed.
D theta.
D theta. Right, in the numerator, we can turn that into 1 minus cosine squared so that we have the same trig function. So 1 minus cosine squared, and then we
Simplify?
how?
No.
Split the fraction, make two fractions. So we're going to have 81 integral of secant cubed, eek, minus secant d theta.
That's what you get if you do it the other way.
Yeah,
It's exactly.
exactly. Yeah, it doesn't matter which way you go.
So it still sucks.
Yeah, it still sucks. Yeah, you're right.
So how did you get sine squared over cosine cubed?
Tangent is sine squared over cosine squared. Secant is 1 over cosine.
Oh, okay.
So we've got 1 over cosine and sine squared over cosine squared.
Both sides.
All right, how do you integrate secant cubed? We've done it twice this semester. It's not going to be on the test. You would use there's two ways. Do you remember how we did it? It was the one. No. Bad answer. Bad answer. So it was the one function that we integrated using ultraviolet voodoo. It's the one time. Let's see, I can't get that little thing. There it is. There it is. Secant cubed. Did you block that out of your mind?
Yes. Yeah.
So we did integration by parts. So there is the antiderivative right there. We are not going to do that again.
Thank you.
Whoa, what did I just do? I wanted to grab that. So control copy, right? So yeah, we're not going to integrate. We won't do it again. We'll spare you. Okay. So integration by parts is how you would do secant cubed. So this will be 81 multiplied by all of this. And then how do you integrate secant? Natural log tan plus sec, or sec plus tan. Doesn't matter. And then integration constant. Distribute the 81. It looks like we just use a pretty clever log trick here, right?
We can.
Holy macaroni.
What long trip? Oh.
I mean, there's a sec plus tan in both of those things. Oh, I guess we don't need a log trick. We just need to know how to add like terms.
That's hard.
Right? We could just add like terms. We have 1/2 log sec plus tan and minus 1 log sec plus tan. Do not use a log rule to do that. So what do we end up with? Yes. Yeah, those are like terms. Oh my gosh. I'm losing my mind. Okay, plus C. All right, there we go. So that's the simplification. Now, we want to get back to x from theta. Since x over 9 is tangent, let's draw our triangle over here. X over 9 is tangent. So tangent of theta is opposite over adjacent, so x and 9. Hypotenuse will be the square root of the sum of the squares. And now we just plug this in. So we're going to have 81 over 2 secant of theta, hypotenuse divided by 9. Hypotenuse divided by adjacent. Tangent, x over 9. Distributing the 81, natural log. Secant of theta, again, that plus C. One more step. Let's see if the grasshoppers can understand. One more step. Tell me if you get this. So the front, that's not a big deal. Here is the next step. And I'm so interested if you agree. Riley, do you see it? anyone see it?
He said it.
What's the question?
How did I simplify it to that? Aren't there some denominators missing?
Didn't you?
Yeah, the 9.
Did you just throw it to the constant or no?
The 9's missing.
Let's see.
Can we just combine those 9s with the constant?
Probably.
Sure. Eliana, you know how? Jared? Log rule?
Yeah, bring the 1/9 out.
Log rule. What is the log of A over B?
A over B.
Oh.
Log minus log of B.
Yep.
Minus log of B.
So let's suppose we have the natural log of the square root of something, and I'm just going to make something different up here. Isn't this just going to be natural log of the numerator minus natural log of the denominator?
Yep.
And the natural log of the denominator is a constant. And so then that constant just gets absorbed into the C.
So I was wrong.
There is a homework question that has this happening.
Oh, wow.
Let's go with the last question.
This is
Will you scroll up real quick?
Yeah. Is that far enough?
Yeah. I thought that the natural log got canceled out.
We partially got canceled out because we have half ln minus full ln. So half ln minus 1 ln gives us minus a half.
and we're done.
Yeah. Okay, so that's an interesting simplification step.
And then we're able to be done with class.
All right, PFD. Do we need to do a PFD? Or?
Yes.
Oh, with linears or quadratics or both? Or?
The easier one.
The easier one?
All right, first let's do this one.
I'm not here.
So, are there any irreducible quadratic factors in this one? No.
No.
Do you agree? Everyone?
Yes.
No irreducible quadratics. You can't agree with yourself. There are no irreducible quadratics in this one. This factor is a linear factor that's repeated. This should be looked at and thought of as x minus 0 squared. That's how you should be thinking about that. So that is a linear factor that is repeated. It's not an irreducible quadratic. So this inside will be rewritten as a divided by x plus b divided by x squared plus c divided by x plus 3. So that's our PFD. So for each power of that repeated factor, we need to have a partial fraction.
And then multiply by that entire thing.
Multiply by the denominator on the left. When we multiply by that denominator, it clears out on the left. Here we're going to have ax times x plus 3 plus b times x plus 3 plus c x squared. Agreed?
Still, why is the b not having another x?
So if you multiply both sides by x squared, that goes away.
Ah, thank you.
And that is why. Convenient values.
-3.
-3, 0, and we need to pick some other convenient-ish value.
0. I mean 1.
Sounds good. So plugging in 0 on the left, plugging in 0 on the right, these two things go away. So we're going to get 3b. So b will be -11. Plugging in x equals -3 will give us -36 on the left. So we're replacing every single x with a -3. So on the right, we get 9c. That tells us that c is equal to -4. Plugging in a 1 everywhere across the entire equation. Plugging in a 1 gives negative 32, and over here we're going to end up with 4a. Plugging in 1 there is going to give us 4b. Plugging in a 1 there gives us 1c. So now we're going to take the b and the c and plug those in to that lower equation and solve for a. So we will have negative 32 equals 4a minus 44 minus 4. So that's going to be minus 48 on that side. Add it to this side, and we're going to get 16 equals 4a. So a will equal 4. Yeah. Any issues? Okay, so a is 4. All right, so now we are going to rewrite our integral then. Integral of 4 divided by x. B is negative 11. So negative 11 over x squared. We're going to write it negative 11 x to the negative 2. Minus 4 over x plus 3 dx. So now we have completed the rewriting. We've rewritten our integrand with partial fractions. Roberto?
So I'm getting a little bit lost on when you start doing your a plus b plus c. So you multiply
This right here?
Yeah, that part.
So we multiply the entire equation by x squared times x plus 3.
And then you got
So it cancels with this. One of the x's cancels to give that. 2 x's cancel to give that. X plus 3 cancels to give that.
okay, I see that. And then from there, that's also where I get a little confused.
So the convenient values are from these denominators. 0 causes that to be 0. Negative 3 causes that one to be 0.
What if you don't see it by the convenient value? How do you do it?
Then you would multiply this all out. So if you were going to multiply this all out and use the traditional method, you would have ax squared plus 3ax plus bx plus 3b plus cx squared.
And then how would you solve it from there?
What's the coefficient of x on the left?
It's 0.
Coefficient of x.
Oh, okay.
Coefficient is 1.
Oh, 1.
The coefficient is the number in front of it. So we'd set 1 equal to 3a plus b. We would set negative 33 equal to that. So b will be negative 11. Let's just write it down. So these are our 3 coefficients. Coefficient of x squared on the left is 0. So that's going to be a plus c. Coefficient of x on the left is 1. Coefficient of x over here is 3a plus b. Constant on the left is neg 33. Constant on the right, right there, 3b. So this tells us that b is negative 11. Plug in negative 11 right there. Add it over here, we get 12. 12 divided by 3, that's going to give a is 4. And then plug 4 in up there, and that's going to be c equals negative 4.
Where are you getting the x squared from?
X squared on the right is a and c. X squared on the left, there's 0 x squareds here.
Oh, okay, I see what you're saying.
The homework kind of like factored it, so it put like, for example, like x
Mhm.
squared parentheses a plus c, and then did that first, which made it a little easier to digest for me.
Yeah, you could definitely do that. So if you want to write an intermediate step right here, you would combine and write this as a plus c times x squared, and then group your x's. So then 3a plus b times x, and then your constant is 3b. Yeah, absolutely. All right.
Could I request a problem?
For the exam?
No, to go over.
Yes.
But you could put it on the exam if you want.
Yeah. That is another, let's do that one. So, or at least, all right, so read it to me.
2 over x, parentheses, x squared plus 5
Squared.
squared.
Okay, so this is we haven't done a one with an irreducible quadratic. This has an irreducible quadratic, so this is perfect. So we're going to take the inside of the integral, and we're going to write this as a over x plus bx plus c over x squared plus 5 plus c d x plus e over x squared plus 5 squared. So that is the PFD. We have to have a fraction for each power of a repeated factor. So the x squared plus 5 is repeated, so we need to have a fraction for x squared plus 5 and an x squared plus 5 squared. One for each. Multiply both sides by the denominator. Yeah?
I don't know if you can tell us this, but would you ever go, like, is there going to be ever a problem where it's more than just 2?
No.
Okay.
Well,
I changed your mind.
I mean, not for an irreducible quadratic, no way. But you could have like an x cubed or something, but not for the quadratic. The quadratic, that would be really hard. So then here,
It wouldn't
let's.
be hard, it would just be painful.
It would be painful, yeah. It would be hard in the sense that it takes forever. So then when we multiply across this one, we have an x and 1 x squared plus 5. One of them cancels. And then over here, both x squared plus 5s cancel, and we just have an x. So dx plus e multiplied by x. Now with irreducible quadratics, it makes more sense to go the traditional method than the convenient value method. So we're just going to multiply out everything on the right here. So we're going to have ax to the 4th. Foiling this, we'll get x to the 4th. And then 10x squared. So then 10ax squared. A 25, but then multiply it by a. So there's the first part. Now we have to multiply this second part. We're going to have bx cubed times x, which is bx to the 4th. Bx, no, let's do cx squared. So cx squared times x is cx cubed. We'll do it in descending order. And then bx times 5 is 5bx, but times another x is 5bx squared. And then c times 5 times x is 5cx. And then over here we have dx squared plus ex. Wow is right.
I hated this problem, and I got it wrong the first time and had to redo it.
At least you got it right the second time.
Yeah. Yeah.
Okay, so what is the power? So let's go through this in terms of highest power first. So what is the power of x to the 4th on the left? 0 equals a plus b. What is the power of x cubed on the left? What's the power of x cubed on the right? X cubed. Isn't it just c? C. Power of x squared is 0. Power of x squared is 10a. And then 5b plus d. How about power? So that was, what was that? 4, 3, 2, power of x on the left. 0. Power of x on the right. No x, right there and there. So 5c plus e. Constant on the left is 2. Constant on the right, 25a. That's it, right? 25a.
So A equals 12.5.
So, so a will be 2 over 25. C is equal to 0, so do you agree that E is also equal to 0?
Yes.
So if C is 0, E is 0.
How come you were able to solve that like that?
If C is 0, plug in 0 here. So these two, we have these two zeros right there. All right, so what's left? What's B?
Negative 2.
Negative 2 over 25. So now we have everything except
D.
D. So D is right here. So 10a plus 5b. So 10a is 20 over 25. That's 10a. Plus 5b, that's minus 10 over 25. That is going to equal negative d if we move the d to the other side.
So it's what, 10 over 10, 25? 10 over 25?
So 20 minus 10 is 10 over 25. Multiply by negative 1, we get d equals negative 10 over 25. So now we have all those things. All the constants solved for. Now we need to integrate.
No.
Feels like we should be at the end of the problem.
Yeah, we should be, but no, we're not halfway down.
We're only halfway done if we're lucky. All right, so,
It was after integrating that it got really weird for me.
okay, so it's a over x. So I'm going to write the original integral as omega. So a over x. So 2 over 25 over x. A over x. And then bx plus c. So bx plus c. So plus bx plus c is 0. So that's good. X squared plus 5. Dx plus c, so then dx plus e, so dx, what's e? 0. X squared plus 5 squared. Dx. All right. What's the very first one? Natural log x. So we have 2 over 25 ln absolute x. What about the second one? Isn't it in log form almost?
Yeah.
So there's a minus 1/25th in front, and then natural log of the denominator. All right, so I'm going to pull the 1/25th, the negative 1/25th out in front, and then in the numerator there'll be a 2x, and the derivative of x squared plus 5 is 2x. So this is the derivative of that. All right, perfect. So now we just have one pesky one. So 10 over 25 integral, and that's x divided by x squared plus 5, quantity squared, dx. And what technique would we use for that? U sub. U sub. So if u is equal to x squared plus 5, du is 2x dx. Divide the 2. So we will have all this mumbo jumbo minus 10 over 25 times x dx. We have a division by 2. Integral u to the negative 2 du. Add 1, divide. So these stay the same. This becomes negative, oh, that simplifies. Negative 1/5. And then this is going to be u to the negative 1 divided by negative 1, so it's going to be plus 1 over u plus c. And then we just plug in u, which is x squared plus 5. Yeah?
That's exactly what I got. When I went through it with the help me solve this, it had this weird thing with a square root in the second bit, which got really confusing for me.
In this second bit right here,
Yeah,
it used the square root thing?
somehow. Let me see
Huh.
if I can find it.
Now you look it up.
I remember that.
You remember that?
Uh-huh.
Oh, that's weird.
So I
You
figured
just have to remember that all of those help me solve this and view an example, those are done by graduate students,
Oh, that explains it.
right?
What about view exam?
They're like sitting down at the pub, right?
You're just.
And they're trying to come up with ways that might be weird but work. I mean, most of the time, I would say 9 out of 10 times the way they do it in the view an example is good. But about 1 out of 10, it's going to be like a little bit suspect. So if there's weird stuff going on and you're not sure what it means, just come and ask me and I'll tell you to do it a different way. All right, let's pause for 48 hours.
48.
Okay, more. A lot more. I don't know how many more, but we'll pause until Monday. Let's do it that way.
Yeah.
So that's
48 hours is 2 days.
That's how many hours? No. That's 2 days. No.
Wait, what are you doing?
Yeah, 96.
I mean, they're putting it in log form,
Are the limits going to be on the...
so they're factoring out the 40 bits. Then they have to put in
I was busy studying for
Oh, I see. Yeah, so they put it in, all they did was this. So all they did, so you know how we simplified, so all they did was take a coefficient and move it up into the exponent.
Of a number.
That is what they did. That is kooky. Yeah, it's very weird. Yeah, so what they did was took the 1/2.
Yeah, if there's no
You know how we
bounds
have 2 over
on
25 up there?
answer, like if it's not like a
So they made it a 1 over 25. So they did this.
They
They,
took a 1/2 and they used properties of logarithms to
Yes.
make it the exponent.
don't do it that way.
It's so wacky. It
That's
doesn't even
wacky.
sure.
Don't do it that way.
But it does get rid of the absolute value, which is, I assume, why they're.
Yeah, that's a reasonable